In this video, we're going to talk about Chapter 3, the Common Network Topologies and Infrastructures. Now, the learning objectives are to describe common network topologies and infrastructures and how to incorporate them into a secure network design. The key concepts are going to be network devices. We're going to delve into physical and logical topologies. We're going to talk briefly about Internet Protocol version 4, IPv4, and IPv6, or Internet Protocol version 6. We also are going to discuss network infrastructures and some of the related security concerns. Now, what is a computer network? Well, the key is it allows organizations to share information and resources that help enhance employee productivity. In the old days, you would have to actually, you know, copy your information to a disk and walk it over to whoever you wanted to give it to, or you had to print it out and, physically hand it to them. And that was the old networking called sneaker net, where you would walk across the floor and hand it to somebody, or you would mail it to them. Nowadays, they decided to start doing networking, and now they are able to send information to coworkers around the world almost instantaneously. One of the cool things about networking is it allowed businesses to streamline inventory management of their data files and their resources. It enhanced communication and collaboration. So just think, in the old days, you wouldn't be able to take a class like this online. You would have to go in person, and I would have to, load it on my computer, these slides from disks, and actually present them one at a time. Nowadays, it's online, and you can hear my lovely voice as it lulls you to sleep. So, well, one other thing we have now is instead of using like big shoe boxes filled with floppy disks, we now have centralized storage servers. We have cloud storage nowadays, uh, where we can utilize this and share data and say, yep, it's on a share, go get it. Mail servers are centralized storage systems where you can send messages to one another. Um, we also have networking enables authorized users to access information quickly and efficiently. Uh, it is networking is composed of different devices connected with common addressing protocols and addressing schemes. Most everything nowadays uses IPv4 and IPv6 as the primary means of addressing. In the old days, there were competing protocols out there. Netware had IPX SPX. Uh, there was Banyan Vines, another competing protocol, and others out there to boot. They had VNS rather, for connectivity to mainframes and terminal connectivity, but most of that was able to be ported over to TCP/IP through IPv4 at the time. So basically, we're going to talk about network topology. And what is a network topology? Well, it references the order and arrangement of all the elements in a computer or communications network. Uh, this could include phones, laptops, desktops, servers, printers, anything we can use. Even televisions nowadays are networked. So these are a lot of different things you can set up on a network topology. So it's all the different nodes that are out there that created. Uh, Now, these computers and peripherals, how do they talk to each other? Well, what we had to do in the old days is we had to establish a common communication method. Uh, this required networking hardware that was added. We'd open up the systems and insert a card that would connect onto the motherboard, and then we connect a cable to it, and then we were able to choose a protocol, and then we would set up IP addresses and IP schemes for that. So we had required hardware, and one of the things was whether or not we had redundancy. If a network was up, it was good. Nowadays, you're not seeing as many issues with networking very often. Um, just the other day in February of 2022, AT&T had a network connectivity problem with the upgrade, and that brought their whole network down. Most of you may not realize this, but most of your cell phones out there are communicating on a digital network with a variant of TCP/IP to allow them to connect digitally and send traffic that way. So instead of using analog voice, most of our cell communication occurs digitally across networks. Uh, Lastly, we're going to discuss, some network diagrams and network maps. And this helps us when we're understanding the connections and communication pathways that exist. So we always map these out. We're going to be drawing these out in class in our labs to see how they do this. And a lot of times you're going to want to have these because they're essential for troubleshooting. They can show you the physical location of your devices in case you actually have to go and tinker with them or replace them physically. And then you can see the logical pathways of how these things are traversing the network. In the advanced networking class, you can get into how all these are done and how to create the routes later on. Or if you've already done that, this should be old hat for you. So, what are some types of network devices? Well, first we see the hub, the punch down block, the smart hub, the repeater, the switch, the router, the bridge, the transparent bridge. It's like something that you just don't even see it's there. You have the source routing bridge, you have routers, and then you have gateways. A lot of these things are pretty much deprecated now, and you don't see them in use very much anymore. So here is one of the simplest things. Many of you may have set this up in your house when you were younger, or your parents did, and they would have, a couple of PCs in the house connected to a router, and maybe you would have a server or a desktop acting as a server and a print server there with some printers connected into your network. And this LAN hub was something very simple because anytime some traffic occurred, let's say from the PC desktop, and it was trying to connect to something on the file server, with the hub, every device on the network would get a copy of that packet. So it was pretty much, everyone got a copy of all the transmission, and that just kind of led to congestion of the wire. So that's why we don't see hubs that much anymore. And that led to the development of the switch. The switch allowed traffic to be coming in one switch port and then be routed to another switch port. This was done with software using a MAC address table that was kept in software. And then if you had multiple switches, it would use something called the spanning tree protocol, which would allow other switches to get a copy of each switch's MAC table. And it would know, okay, I know what port to send that packet to, or I know to send it to, this switch, and then that switch would then send it to the exact port without having to send a copy of those packets to any of the other ports that are out here. So an example of a switch deployment would be if we have 3 different layer 3 switches and some layer 2 switches out there. The workstations will connect to layer 2 switches. Layer 2 is just the MAC address. Layer 3 is when you incorporate stuff called VLANing, and you can have stuff out there for layer 2, layer 3 switches to do that. So again here, everything comes on here. If you're trying to go from something in the top oval here to something in the bottom oval here, like one of the workstations here, uh, the oval in the middle would not see any of that traffic other than it just being passed through that L3 switch. So the top L3 switch would then hit it to the middle L3 switch, which would immediately forward it down to this L3 switch, would then forward it down to that L2 switch, and then it would be directed to the proper workstation based on the port and MAC address it was. So how does this all work? Well, we have the 802.E, based on the IEEE Ethernet frame 2 type frames, or frame 2. Um, so how these get routed is we have the destination MAC address, and this is the remote hardware address based on the MAC address of that system, the source MAC address where it's originating from. And then we have the Ethernet type, which is the 0800, which means it's TCP, or yeah, and then or IP packet. And then here we have the payload, and this is the IP address where there could be IP, ARP, IPX, whatever it is out there. And then at the end you have the CRC checksum, which validates the integrity of a packet. Remember back in the first chapter we talked about integrity? Well, this validates that the packet is whole. Here's something that might look familiar to some of you. This is a early home router. It would have 4 ports in there, and it was wireless also. So you had a wireless router. You could connect 4 physical devices to it, and then you would connect it to your internet connection, and that's what that looked like. So a topology for this would end up being you have your computers and your server connecting in, and then you would have that wireless thing could act as a border router connected to the internet. You could also have a firewall out here or something like that. But this is basically an example of a routed network where we have an interior router where the computers are on one subnet, the server's on another subnet. Uh, the Between the internet router, interior router, and the border router, that line right there is another subnet. Uh, the server off of the border router is on its own subnet, and there's a computer down there off its own subnet. And between the border router and the firewall, those two interfaces are on their own subnet, and then the firewall is on a subnet that is part of the internet. So that's how all this communicates, and these are all connected, and they all share routing tables through a number of different things, usually most likely through OSPF. Yeah, I guess I'm not boring. My dog just cried out. So here's an example of a switch deployment with a Mac bridge. Now, this is something that you only read about in your history books. You're not going to see this really ever again. Um, so I don't want to spend a lot of time on it. But basically, all of these things are basically essentially on the same physical LAN. They forward the packets like it's a fancy hub. And so everybody gets all the same traffic between the two things. So it just forwards things on. There's no routing here. Uh, all of these devices could technically be on the same network subnet, and they're just separated by that. If you're connecting two different networks with two different subnets, The device between them is referred to as a gateway. So if you ever do an IP config in Windows or IF config on Linux or Unix, you can see that there's a default gateway setting there. And that's where all routing packets, so for this network, all these systems would be sending stuff to this interface as its default gateway. Conversely, all of these servers on the left-hand side and PCs would be sending it to this interface here as its default gateway. So that's what those are used for there. It's just basically a gateway is just a router. Uh, so what's the difference between logical and physical topologies? Well, physical topologies are the way, they're physically connected. The wires, the cables, the wireless, um, all of these things. What physically enables them? Are they fiber connected? Are they using, network, wireless, whatever? Uh, Now, one thing to remember, all networks have physical and logical topologies. So you have both. So you got to understand the difference between a logical connection and a physical connection. So, yeah, that's the wire that's out of the back of your computer, or the wireless card. That's the radio waves being sent to your router. Those are your physical topology. Now, wire topology is the physical wires between the devices, and a route is the pathway that the communication packets travel within the wire connection. So those are some things you're going to have to look at there. Logical topologies, these are governed by policies such as ACLs, routes, VLAN tags, um, something other than the physical connectivity. Uh, these are done by software enhancements to the network that allow the computers to be focused on how to share access and resources in a controlled manner. In the old days, we had what was called bus topologies. Now, if any of you have ever seen a cable TV network or something, or some of these connectors that come out of your wall or apartment that you hook up your TV to, if you have a direct TV and you see those big coax cables, well, those are basically the same type of cables the original networking was on. Those are called, you know, just coax. There was something before called AUX where you had to use vampire clamps on it, which were like these teeth-like things. You would just sink into this very rubbery thing and it would grab on and make join the network that way. But these were actually little things where you had a BNC connector, and then on both ends of the cable you would have to have terminators, which were insulated little ends that would absorb the electrical impulse of the packet. So node 3 sends out a packet here. Uh, if it's trying to go to like node 4, uh, it would eventually hit node 4, but the rest of the signal would still travel down the line to terminator B and terminator A in the other direction. So all the nodes on the network receive that same traffic. So that's what that is. Next thing was the ring topology. And instead of having terminators, this was a closed loop system. So it's like a lasso. It would spin around and around, and there would be like a little packet on there called a token. And the token would be sent between different systems. There'd be a single thing. And I don't know if you've ever seen like those things where you sit around in a powwow type circle, and you have like, I don't know if you were in Boy Scouts or Indian Guides or Girl Scouts or Brownies. You had what was called the talking stick, and only the person with the talking stick was allowed to talk. And then you would pass it to the next person, and that would go around in a circle. That's essentially the same methodology of what token ring is. So it's unidirectional. It goes one way. The only person or the only device can talk is the one that has the token, and then it passes on to the next device. But once it's put on the wire, everyone on the wire hears that. All right. So after that, we started getting a little bit more complex, and we started developing star topologies. And this is where you start seeing that switch and WAN come in, where everything started going into one central device, and then it would branch off from there. So it resembled a star or a cluster. So each ca- so the cables weren't connected to each other device, like in the token ring or the bus configuration. Uh, all these devices now connected to a central networking device, like a hub or a switch now. And this is what you're seeing nowadays. Uh, and that's our current state of networking. They're all basically star topologies. They get more complex, but breaking them down, each local one is a star topology. All right, so mesh redundancy is another type. Um, and you don't really see this as much, but uh, in this, the way it's depicted here, where you see the devices are connected to each other directly, uh, you know, essentially this is something, where every device would have, like this laptop up in the upper left hand corner would have to have three network cards. The one in the top center of the top of the triangle uh, would have, five network cards in it. The laptop on the right, three. The laptop in the left middle would have, five also. So you don't really see this as much anymore. But it allowed for full on partial connections between devices. Um, this you see this more like this in a logical topology than a physical topology nowadays. So, all right. Physical topologies again. Now we get to the wireless topology, and there's minimum wiring here involved. Has the wireless routers connected into the LAN switch, which has everything else wired into it. And then all the other devices that are connected to the wireless lane are connected to it via a radio signal. And they use the radio waves to act as a medium of exchange for that communication. So when you're doing wireless, you at least need to have one wireless router present. All right, logical topologies. Now these focus on the connections and permissions themselves. Uh, Here's where you get into configuring the switches and routers and other devices on your network, your firewalls and such, to create those separation of duties and access. Um, the setup is to, kind of restrict access to data and resources to only those systems that need to get access to that. So let's say you have, your all your private files, your password files, everything like that on your server. You don't want to have that exposed to the internet where everyone can connect to it, do you? Of course not. So here you would use mechanisms on your networking devices to create and limit access to only those that need to access those certain systems. Um, so what you can do, the segmentation kind of protects employees from accidentally accessing, altering, or deleting information that they shouldn't. Um, this is also something that it helps in legal compliance by creating what is a concept known as least privilege. Least privilege means that you have only the minimum rights needed to access that data for your position or your role. And it also helps create a separation of duties. So You have permissions and stuff like that. And segmentation also helps in hiding assets. Now, we're not talking about hiding assets from legal or anything like that, but we're saying, we don't want, you know, all the employees to be out there being able to access uh, stuff like your HR data or anything like that. So you can create those segments where like only HR personnel are able to access HR data, or you're only able to review your HR data and stuff like that through a portal and stuff like that. So that's there. So here we see a logical topology, and up here we see a web server in what is called a DMZ, or a border network or a perimeter network. A lot of times in modern times, you're not seeing as much of this terminology of a demilitarized zone anymore. You'll hear people say DMZs, uh, but as more and more people are having to get involved in information technology and information security, they do not understand certain nomenclature. So if you say it's a border zone or a border network or a internet connected area, they're more likely to understand that versus a DMZ or demilitarized zone. As you can see, we have logical topologies that also break up into a server LAN where you can put all the servers on its own local area network, logical network. And we also have a internal LAN where you can put your desktops and computers on that. And of course, on the internet, laptops, desktop PCs, and all the bad stuff can be out there on that. So, what creates logical topologies? Well, the first thing are subnetting, okay? And subnetting is created at the OSI layer 3 network layer. And these are out there that help, set all that up. And you can have different subnets out there. Now, VLANs are associated with these, but these are created at layer 2, and these are created at the data link layer. You would create a number of assets and provide them with what's called a VLAN tag. A VLAN tag is nothing more than a set of uh, letters and numbers that are unique to that VLAN. So you can start off and number them like 0001, 0002, till you get to uh, FF, FF, if you want. So most of them are hexadecimal, by the way. So that's why I went with that in letters. So that's why I say it's numbers and letters, because it's really hexadecimal. All right. All right. Here's an example of what we see how a VLAN can be partitioned on a network. Each floor here has its own subnet and switch. Okay. But there's an accountant sitting on every floor. And each of those accountant's machines has an accounting VLAN tag. Same with marketing and same with engineering. So these are all routed in the same VLAN group, even though they can be on separate network switches. Okay. And separate network subnets even. So now we're talking about differences for routing protocols. Well, we have two things out there, IPv4 and IPv6. Most everyone is still familiar with IPv4. It's the predominant protocol on the internet. Everyone still uses it. It's a connectionless protocol, IPv4. And you're like, wait. TCP/IP is connection oriented and UDP is connection. That's true, but we're talking about the IP portion of the protocol. IPv4 is technically connectionless. TCP is where sessions get set up. UDP, of course, still is connectionless too. These operate at the layer 3 of the OSI model, and they're the foundation of the TCP/IP protocol suite. So we have that there. Now, IPv6 came about. If you read the book, you're going to see that, oh no, we're running out of IPv4 addresses because of all the plethora of IP, addresses running out IPv4. So what they did is they created IPv6. They just went ahead and skipped IPv5 and went from a 32-bit, instead of going 32, they skipped the 64-bit addressing scheme and just jumped to the 128-bit addressing scheme. This increased the address base to where they said this equals to every star that can be counted in all the known galaxies at this time. That's what they're comparing it to. It offers more efficient routing. It helps reduce the management requirements for these systems. It offers a built-in quality of service uh, protocol passage, component. There's better security. It can be dual stacked. You can use IPv6 for tunneling and network translations between different segments. So if we look in data notation, you'll see like an IPv4 address is like 192.168.12.153. And when you convert it out to binary, you have 153 of 8 octets. So right there is the 153. There's the 12, etc., all the way down. Now, in hexadecimal notation, you'll see this is IPv6, and this converts into hex. So we have a lot longer address compared to the IPv4. So 64 characters long. So you can count more than 64 there. It's 128, I think, totally. So that's 32, and this is supposed to be, I think, more than that. I think it's shortened because there's some double notations in there. So instead of dots, these are colons, by the way. So make note of that when you see IPv6. Internet Protocol Security and IPv6. IPsec is a mandatory component in IPv6. It can be implemented in IPv4, but it's natively used to protect IPv6 data. Now, IPsec in IPv6 uses authentication header and an encapsulating security payload ESP extension header. Now, the internet standards that use cryptographic security services to provide this helps provide that confidentiality, the data origin authentication, and data integrity. So we know that these are still good for that. All right, so we have some examples of network infrastructure related security concerns here. So when we break it down, we have, a work group. We have the small office, home office setups. We have client server setups. We have the differences between LAN versus WANs. We have thin clients and terminal services and HVDs, etc. We have remote access control or remote access, remote control, VPNs, and boundary networks. So all of these areas are different things of concern. Here is a typical work group. This is something you might see at your home or your home lab. You have a switch there, you have your workstations there, you have your laptops, wireless router, maybe printer setup, you have your maybe cable modem or fiber entry in there, or whatever you have your internet connection here, and you have everything connected in and pipe through that to go out to the internet. That's a typical work group. All right. A small office, home office. These are small businesses. Usually see these set up in there. A lot of times you may see these deployed in houses, uh, you know, portable buildings, lease space where people sit there and just do small office work. Um, these may be designed as a client server setup or a work group setup with no server. Um, these systems have more sophisticated networking equipment, which makes them more secure than the typical work group. And usually they have firewalls, antivirus software, anti-malware software, and basic auditing for that. All right. Client server networks is stuff where you're starting to see where you get your domain controllers or things like your central authentication in there, where you designate servers, computers become servers, and others become clients. And these environments are more likely to use hardware and appliance firewalls. Uh, they employ centralized authentication that allows for single sign-on, and they are more secure than a small office, home office, or SOHO, or workgroup network. All right, and here's a picture of a very basic client server network. Now, where I work currently, uh, it is much more complicated, but basically this is a simplification of most any client server environment that's out there, where you see a number of different things connected to switches. They have web servers, multiple firewalls out there, and all of that prevent and protect the network and segment it. So I've used terms out there like LAN and WAN. A LAN basically is a local area network. These are located within a single geographic area. Segments and links are owned and controlled by the organization. So that means the wires connecting all the system together are owned by the organ that is their network. It doesn't contain or use any leased or externally owned connections. So that's all part of that. So everything internal is on the LAN, and the network owner is responsible for ensuring that the network security is enforced, or all security is enforced on the LAN. Now, WAN, let's say you can connect your LAN to a WAN by adding an internet connection or an external router. Um, they're not limited by geographic boundaries. Uh, you know, everything on the internet, whether you're going from one place to another, you're traveling through a telco. If you start doing trace routes, you can see, you might be hitting, AT&T, you might be hitting Verizon networks, you may hit CenturyLink networks, and all that. And so we see a lot of different things there. Um, we see that as you traverse all these different networks and telcos for WANs, you might also be, connecting through links of other businesses. Like say if you're leasing something in a building and the building has centralized connectivity to a internet or something, you might have to, rely on the telco or a building connection to go out to the phone system or telco or whatever it is for that. The only way you can secure your information is to encrypt it before you transmit it. And the leasing entity selects a secure telco. So whoever you're going to use as your ISP, you got to make sure that they have a good service level agreement, which means that they will have a certain amount of service of uptime for you, uh, and a provide enough security to say that nobody's going to be tapping their lines, unless of course it's somebody like the NSA or something like that. So they can't prevent that without a warrantless. You don't want them to do a warrantless tap. We have talking about thin clients and terminal services. All right, in early computing models, there was a centralized computer core. You had a terminal, and you typed anything you typed in there. The characters were just basically sent to a larger mainframe. It was just basically a dumb terminal. Had no computer processing on it. It was basically like a television and keyboard out there. There was no local storage or anything else on there. It just, you know, typed it in and it would go to character by character to the server. There was no local anything on there. So there. With the advent of PCs, the workstation computer offered some local processing and local storage. And then they started doing client server models. So we used to have servers out there. And you could, save set mirror, connect down there. You still see a lot of this today. You might be working on your homework in Microsoft Word, and you save it to your OneDrive or your Google Drive or whatever you want to do. That is an example of a client server model right there. You provide it there, you store it on a centralized space. There you go. That's a client server model for you. Uh, Also now in a modern environment, like in a lot of companies, they don't want you to have something to leave their network. So they offer servers where you basically set up a screen and it looks like your laptop. It's called a HVD or HVA where you can run it and you're actually running the application through a remote session uh, as a client. And it's a thin client. It emulates basically the terminal system of the past. Nothing gets stored locally there. Everything gets stored on a central location. You can't copy anything down to your local PC. You can only just see what the screen is. So now we break it down into other concepts such as remote control, remote access, and VPN. So remote control, this is like where if you call your help desk or somebody and they connect to your system and they're out there moving the mouse around and fixing something in the background through a session, basically they used similar thing to what that HVD was for you. They connect to you using some kind of remote desktop protocol to allow that connectivity. They can use like WinVNC or any X Windows or any of these other protocols that are out there for that. Remote access is something that is used to connect network resources using a WAN link. So I want to, RAS in, I can use a dial-up modem and call into my network or my ISP. Um, these were typically used in days of old. And that eventually evolved to when we all got our permanent internet connections, our cable modems, our fiber drops, or whatever we have. Nowadays, however we normally connect in. Uh, Nowadays, if we want to connect to our places of work, we use what's called a VPN. And it's a network that encapsulates packets destined for the remote network. So it connects your remote systems into that distant LAN for you. So here is a thing before the internet connected. Uh, we had resources connected to the internet, remote client, and they were, oh, I can see you, but I can't get into my internal stuff. How do I do that? Well, they devised a number of things out there, but eventually they established VPN connectivity where a virtual connection occurred and it was just between the remote PC and the private LAN, and it allowed this, this packet would go across the internet, but you know, it would like be a smaller packet inside of it. The way I like to describe this is, have you guys ever seen those trains that carry cars in them? Well, at like say someplace like at a uh, factory, They load a bunch of cars into a car carrier, 18-wheeler. That 18-wheeler drives across the highway and gets to the dealership. And then it parks there and it unloads all the cars. Well, that's kind of what happens with all the packets and a VPN connection. You know, packets get loaded into these other packets and they get shipped off to the remote site. Back and forth they go. What are boundary networks now? Boundary networks, this is the edge that touches another, one LAN to another LAN or one LAN to a WAN. So this is a subnet at the edge of a LAN. Um, it is used to isolate, you know, programs, research, and deployments from private LANs to the public LAN. Uh, a lot of times these are referred to as demilitarized zones. I like to say perimeter networks nowadays because the DMZ sometimes has a negative connotation for those who might be in some areas where there's a war zone and there has been area of demarcation where there's there, but basically uh, from the inside to the other side, it's considered a hostile environment. Uh, so hosts on here are allowed to reach into both, but are not. An extranet. This is a boundary area that hosts resources that provide limited access to a group. Say, if you ever, have to log into something at work and you just go into a web portal and, you log in, you go through your credentials, and then it lets you launch like a little virtual app, like, like your time card or something. I don't know if any of you use OneLogon. Uh, and then once you logged in on OneLogin, you can launch Canvas. That's an example of an extranet right there for you. So boundary networks and DMZ deployment options. Uh, well, there can be a screen subnet using a 3-home firewall. So these are some firewalls out there. Some are multi-homed. So 3-home, multiple homes on there. This allows for segmenting to occur for an internal connectivity, a DMZ or perimeter network connectivity, and all that. Um, and then the other thing is N-tier development, where you have multiple firewalls, and if that one firewall is breached, they can only access what's in that perimeter network and not the internal stuff. In the 3-home firewall, if they somehow breach the firewall, they would be able to access everything internally. So the N-home has multiple firewalls configured, and there is multiple areas out there which uh, would have that to be tiered in multiple places. All right. So here's an example of a firewall that is a screen subnet with a 3-home firewall. So the firewall has a private LAN and the DMZ extranet. And this is kind of a hard explanation, but you have one connection. It should actually show 2 different connections here. One connection here, one connection here, and then one connection out to the internet. But it's trying to show you that, this is where they have uh, the connection for how it connects across the 3-home server. Here's an N-tier deployment where you see the firewall, the DMZ, and another firewall here, and then behind that other firewall is the private LAN. So if one firewall gets breached, then they have another firewall to try and crack into. So in summary, we've covered network devices, physical and logical topologies, touched on IPv4 and IPv6, and talked about network infrastructures and other security concerns. Hope you enjoyed it. and hope you get a good rest after this lecture.